This is part two of periodic trends. I was just talking about what happens when you go down the periodic table. So when you go down the periodic table, well, we have the periodic table right here. Let me draw it real quickly. Oh, that's horrible. Let me go straight down. Something like this. Okay. When you go down the periodic table, what happens to the size? What happens to the atomic radius? The atomic radius, as you go down the periodic table, you can probably guess this, it increases. And it increases because each time you go down a level, like these are periods in the periodic table, each time you go down a period, you're going down, down, down in the same group. Each time you go down a period in that same group, you're adding another energy shell full of electrons. I think that's what I was doing in this previous little video, or I'm sorry, in the previous little slideshow where it showed the different shells and so forth. Yeah, that's what I was talking about there. You get a new shell every time you go down a level. So it makes sense that when you're considering atoms in the same group, or elements in the same group, as you go down each step in this group, your atomic radius will increase because you're getting another shell added on. So, for instance, if you have an atom like this, the very top, which is hydrogen, and you go down one level, then all of a sudden you're getting another shell that's full, well, at least has some extra electrons there in that next shell. So it makes sense that this atom went from this size to now this size, which is now bigger, so the atomic radius increases. Okay, so what about our other trends? What about something like, let me just fill this in here because I don't have it. Let me put this back here. Atomic radius going this way to that way. Atomic radius across here from left to right, the atomic radius increases. I'm sorry, decreases, just kidding. Decreases because of the higher effective nuclear charge and so forth. So what's about ionization energy, which is the energy it takes to rip off an electron from an atom? Well, I'm going to just tell you, and then we're going to see why. It increases as you go from left to right across the periodic table. And the reason it increases is because as you go from left to right across the periodic table, the atom is getting smaller and smaller and smaller. It's getting squeezed because it's got higher effective nuclear charge on the right-hand side compared to the left-hand side. Each time you go from left to right across the periodic table, you're getting more and more effective nuclear charge on those outside electrons. So they're being held tighter and tighter. So it takes more energy to rip away those electrons since they're being held tighter and tighter and tighter as you go from left to right across the periodic table. It makes sense. It's held closer to it, so it's harder to rip it off. So it requires more energy. Right. Now, as we go down the periodic table, the ionization energy decreases. It decreases because of shielding effects. And by shielding effects, I mean that electrons shield this outer electron from being held as closely as these inner electrons. It has less effective nuclear charge, but as you're getting bigger and bigger and bigger, I'm sorry, I should not say that it has less effective nuclear charge, because technically all of these elements in this group right here, they all have the same effective nuclear charge for the outside electrons. But this nucleus does not have the same effect on the outside valence electrons as when they're bigger. So when they're bigger, there's a less of a pull towards this nucleus right here. These electrons shield the nucleus from the outside electrons, and so those electrons are easier to pluck off. In fact, this guy over here, francium, is really easy. That's so easy to take an electron away from francium. It's not even funny. Okay? So ionization energy decreases as you go down the periodic table. Up here is the highest, down there is the lowest. If you just take any random group in here, let's just say this group in here, as you go from the top to the bottom, it also decreases. I'm just making sure that you understand that as it goes from the top of any group to the bottom of any group, the ionization energy decreases. Okay. So the next trend is maybe the least important, but we're going to talk about it anyway. It's called the electron affinity. The electron affinity, as you go from left to right across the periodic table, it increases. It increases, surprise, surprise, because of the higher effective nuclear charge that the electrons feel, especially the valence electrons feel towards that nucleus. The nucleus is just more attractive as it has, as it's pulled all of its electrons towards it. It's just more positive glow. Let's just compare something like fluorine. Fluorine's got 1, 2, 3, 4, 5, 6, 7 protons. I'm not going to draw the neutrons in. And it's got 1, 2, and it's got 7, 1, 2, 3, 4, 5, 6, 7 electrons in the second shell. I'm just drawing it out right here. And there's 2 in the middle. Okay. And this is a this is very expanded. It should be just a point for the nucleus. Anyway, compare this. Oh, look at all that charge. It's crazy attractive. Crazy attractive in here. Crazy, crazy, crazy attractive. Compare that to something like lithium. Please. Lithium only has 3. Loser. Lithium, it has less electrons to block it, well, from any passing by. I'm going to do a passing by electron right here. So here's a passing by electron. And where is it going to go? Is it going to be pulled more towards here, or is it going to be pulled more towards there? Well, check out this positive charge, yo. This is going to be so attractive to this electron compared to this positive charge. This is like nothing. True, these electrons do shield this electron to some extent, but this positive charge overcomes that. So the electron affinity increases as you go from left to right across the periodic table. Same kind of logic applies for the going down the periodic table. So if we go down the periodic table, the electron affinity, well, what would it do? It would decrease as well. And in this case, it's because there's a larger distance between them. So here you've got that's fluorine. So below fluorine, what is below fluorine? What is below fluorine? Come on now. I thought I was a better chemistry teacher than this. Below fluorine, I have to look this up. Chlorine, of course. Doi. Chlorine's below fluorine. Chlorine looks like this. It would have another shell on top of it. So, and it would be full of electrons. In this case, that extra distance and the extra repulsion from all of the extra 1, 2, 3, 4, 5. Yeah, that's good. And there would be, of course, an extra few protons in the middle here. Even though there's a larger amount of protons in the middle here, because there is extra shielding going on and there's an extra distance between the protons and a passing by electron, then this electron would be more attracted to something like fluorine rather than chlorine. Okay? So as you go down the periodic table, the electron affinity decreases. I should say affinity right here. So those are all the trends. Hopefully this made sense, and you can kind of order elements in the kind of like the ranking of the highest, let's say, atomic radius to the lowest atomic radius if they're in the same period or if they're in the same group. And you can do that for all the trends, hopefully. The trends are great because they explain a lot. Mostly it's just about the insight for effective nuclear charge. So I hope that made sense. If not, email me. I'll talk to you later. Bye.